What if we could control an invisible force? I'm talking about a special kind of light, one that can disinfect our water, see things at the nanoscale, and even communicate in ways that sound like something out of science fiction. Well, that's the promise of UVC light. And today, we're diving into a major breakthrough that finally lets us control its incredible power at mind-blowingly fast speeds.
Okay, so to really get why controlling this invisible light is such a complete game changer, let's take a quick look at all the amazing things it can already do.
The truly incredible thing about UVC light is just how versatile it is. We're talking about a massive range of applications. It can help us create these super detailed images at the nanoscale, but it's also used for something as fundamental as sterilizing our water and air. It's a real workhorse in biomedicine, for studying the tiny dance of molecules. And get this, it can even be used for communications in really tricky situations, where signals literally have to bounce around corners to get where they're going.
So, the potential here is it's enormous. Which brings up a really obvious question, right? If UVC light is this useful, what's been the holdup? Why isn't this tech, everywhere already?
Well, the answer really comes down to what researchers call the generation gap. And for years, it's been this nagging two-part problem. See, it's been unbelievably difficult to both create UVC light efficiently and to detect it, especially at the insane, ultra-fast speeds we need for all these next-gen applications.
All right, let's break down that first hurdle, the source. The tools we've had just haven't been quite right. On one hand, you've got things like excimer lasers. Sure, they're powerful, but they are huge and they guzzle energy like crazy. Then on the other hand, you have UVC LEDs. They're nice and compact, but they just don't have that high-intensity punch that's needed. So what we've been desperately looking for is that perfect sweet spot, something compact, efficient, and powerful.
And this is where our story gets really good. A team of researchers from the University of Nottingham and Imperial College London came up with this absolutely brilliant integrated platform that solves both problems at once. Not just generation, not just detection, but both, all in one elegant system.
Okay, so first up, let's tackle how they solve the source problem. The concept is called cascaded second harmonic generation. Now, I know that sounds super technical, but just think of it like shifting gears in a car to get more speed. They start with the common lower energy laser and they upconvert it. They basically give it a boost of energy, not just once, but twice, to create this rare super high energy UVC light.
So here's the play-by-play. It's actually a pretty neat three-step process. Step 1, they start with a totally standard near-infrared laser pulse. You see these everywhere. Step 2, they shoot that pulse through a special BIBO crystal. This essentially doubles its frequency, turning it into visible green light. And then, for the grand finale, Step 3, that brand new green light immediately zips through a second crystal, a BBO crystal, which doubles its frequency again, finally creating the exact UVC light they were after.
And here, you can actually see their setup. Now, I know it might look a little complicated with all the lenses and mirrors, but the really key takeaway here is that this entire up-conversion process, this whole thing happens in a pretty compact system, and that is a massive leap forward from those giant, power-hungry lasers we were just talking about.
So the big question is, how well does it actually work? The answer is, incredibly well. They managed to hit a 20% conversion efficiency. That means a fifth of that initial infrared light successfully becomes useful UVC light. For this kind of setup, that's a new milestone. It's what makes this whole process not just cool, but actually practical and powerful enough for the real world. And you don't have to take my word for it. Professor John Tisch, one of the lead researchers, said it perfectly. He called the high conversion efficiency a significant milestone and a foundation for scaling the system into compact sources. So long story short, they've pretty much cracked the creation problem.
But remember, creating the light is only half the battle. Now we've got to talk about the other part of the problem, the sensor. And the challenge here is just immense. How do you even see a pulse of light that lasts for only 243 femtoseconds? That's quadrillionths of a second. It's an impossibly short amount of time. Well, the solution they came up with involves a totally new class of ultra-thin 2D semiconductor materials.
The real magic behind their new sensor comes down to two pretty remarkable materials. You've got gallium selenide, and then its oxidized form, gallium oxide. These are the super thin 2D materials that are the absolute key to building a detector that's fast enough to actually catch one of these fleeting UVC pulses.
Okay, but here's where the story takes a really cool turn. As the team was testing out their new sensor, they discovered something they weren't even looking for. A property that made their detector even better than they had ever imagined. What they found was that their gallium oxide sensor had what they call a superlinear response. Now this is really fascinating because usually sensors get less efficient the more light you blast them with. They get saturated, but this one, it did the complete opposite. The more UVC light it received, the more efficient it became at detecting it. That is an incredibly desirable and super rare property for a sensor to have.
Professor Amalia Patinet, who is the lead on developing the sensor, summed up the whole achievement perfectly. She said, "This work combines, for the first time, the generation of femtosecond UVC laser pulses with their fast detection by a new class of 2D semiconductors. So you see, they didn't just solve one problem and then the other. They build an integrated solution that solves both together in one fell swoop."
So there you have it. The generation gap has been bridged. We can finally create and detect these ultra-fast UVC pulses using a single integrated platform. So what does this actually unlock? Well, what we're really talking about here is the beginning of a whole new era for UVC technology.
To prove it wasn't just theory, the team actually built a working communication system. They sent a real message encoded in these UVC pulses. But that's really just the beginning. This tech could lead to things like super-resolution microscopy that can see things far beyond our current limits, much more advanced ways to process materials, and even more sensitive ways to monitor our environment.
And believe it or not, it gets even more futuristic. One of the researchers, Ben Dews, pointed out that this work helps pave the way for communication between autonomous systems and robotics. Just think about that for a second. Imagine self-driving cars or swarms of drones communicating with each other instantly and securely using tiny pulses of invisible light.
And here's the kicker. The thing that really turns this from just a cool lab experiment into a potential revolution is that it's scalable. The manufacturing process for these new materials is affordable and can be scaled up for mass production. This was never meant to be just a lab curiosity. It's designed from the ground up for the real world. Another researcher, Tim Klee, really captured the bigger picture when he said, "A compact, efficient, and simple UVC source will benefit the wider scientific and industrial community, stimulating further advances." And that's exactly what this is. It's a foundational technology, a tool that's going to empower a whole new wave of innovation across countless different fields.
So, when you put it all together, we're left with this incredibly powerful new tool in our toolbox, a way to precisely create and see these ultra-fast pulses of invisible light. And that brings us to the most thrilling question of all, the one we get to ask about the future. Now that we can finally control UVC light at the speed of femtoseconds, what are we going to build with it?